Our project is talking about polycarbonate. Our group consists of 3 persons, myself, Carol, then David, and Daniel. What is polycarbonate? Polycarbonate was first discovered by Alfred Eichmann in 1898. Polycarbonate is a good material choice in industry, not only due to the characteristic, but also because its processing is environmentally friendly and it can be recycled. Polycarbonate has a high-performance polymeric material comprise the family of engineering thermoplastic. Like you can see, this plastic is transparent, and we just added some color, but polycarbonate is originally a transparent sheet. Like you can see example on this picture. Let's go to the structure of polycarbonate. Talking about the structure of polycarbonate, polycarbonate consists of 2 main aromatic rings, 2 aromatic rings, and 1 carbonate, like benzene, 2 benzene. And that 2 aromatic ring is calling biphenol. And the other one is benzene. Like talking about biphenol, the biphenol consists of 2 rings and phenol group and consists of 2 phenol group. Propane bond to the para side on the ring has a raised possibility of health concern in recent time. The melting point of 158 degrees Celsius, the molecular weight of 228.29 grams per mole. The hazard, polycarbonate is a corrosive, irritant, it has a health hazard. Let's go like talking about the synthesis. The synthesis of biphenol start with a single primary reactant cumene, benzene ring, like you can see here, and isopropyl group, like benzene ring and the isopropyl group on the top, produced from a crude oil. And now let's talk about David will talk about the oxidation.
Yeah, so to start off the process, there are two main processes that the cumene molecule need to go through until we can actually form the BPA molecule, which is the monomer of polycarbonate. The first step is an oxidation. So this begins by creating a free radical form of cumene, as you can see listed on the right, where the internal carbon of the isopropyl group becomes a radical. And that cumene radical bonds with oxygen here because I'm not a greenskeeper on a golf course, so I don't have any manganese laying around, so we have to use air. And what's formed from that reaction is a cumene peroxide radical. As you can see, the oxygen has the radical on it here. Then, through the second step of the propagation step of this free radical reaction, the cumene peroxide radical attacks another cumene molecule, and the products of that are CHP, which is a cumene hydroperoxide, which is the next molecule that we need for the next process, and then it regenerates another cumene radical to keep the reaction going. It's good to note that in industry this is performed under high pressure and high temperature to allow oxygen to be a good enough oxidizing agent here. The next step of the process before we get to the formation of BPA is the cleavage step. Now, this cleavage occurs under an acid catalyzed hydrolysis of the CHP molecule. So what first happens is an acid, which usually in industry is sulfuric, um, donates a proton to the terminal oxygen on the peroxy group on the cumene molecule, and which forms a water. And as we know, water is a good leaving group, and good leaving groups leave. And then something interesting happens. The benzene ring migrates to the oxygen and creates a bond there and leaves a carbocation on the internal group of the isopropyl. And then, I guess how good leaving groups don't do is it actually comes back and it rebonds to that carbocation, and you're formed with this molecule here on the left. And then through a reversible reaction, you get a proton hop from the water that recently bonded to the carbocation to the oxygen that's directly bonded to the aromatic ring. And then, because this is an acid catalyzed thing or reaction, you regenerate the acid in this step by losing a proton, and then you get decomposition of the molecule into phenol, which is the benzene ring with the alcohol group on it, and then acetone, which is the ketone here. Something to note is that during the cleavage process, a fairly prominent side reaction take place where the CHP is turned into a molecule called AMS, or also known as alpha methylstyrene. And alpha methylstyrene is essentially a dehydrogenated version of cumene, where one of the carbons on the isopropyl group has a double bond. And in industry, this molecule is recycled through a reactor where it's hydrogenated to reform cumene, and this can be used to recycle cumene back through the process of oxidation and cleavage to increase yield of BPA farther down the line. Now, once we have the phenol and acetone, we can finally go to form BPA, and Daniel's going to run us through that.
Yeah, so once the cleavage step is done, we have phenol. And if we mix that phenol with acetone in a 2-to-1 ratio, an electrophilic aromatic substitution will occur to get us to the BPA monomer. So like any other electrophilic substitution, we start with an electrophilic attack, which breaks the double bond, and then the molecule is deprotonated to restore aromaticity. Now, we know that alcohol and phenol is an ortho-para directing group. So we can form an ortho byproduct, but that is undesired. So it's recycled back through the reactor until we get mostly the para product. From there, we can react it with phosgene gas to form the BPA polymer, polycarbonate. But if you pay attention to history, you know, phosgene is pretty nasty stuff. It was actually used in World War I as the premier chemical weapon. So you got to be careful with that when you're making the polycarbonate. So in the presence of a base, the biphenyl A will have its protons stolen by the hydroxyl groups. This makes the BPA monomer negatively charged, so it attacks phosgene's slightly positively charged carbon. This makes a chloroformate. And then the process repeats itself until you form a polycarbonate. Now, that polycarbonate has become so prominent in our lives because of its unique characteristics. It is cheap and easily injected, molded into parts, so you can form really unique shapes for pretty cheap. It has a very good strength to weight ratio, so you get high impact resistance and scratch resistance. It is an electrical insulator, and it actually transmits light better than glass. This leads to its applications in electronics fairly easily. So LED bulbs, the sheathing on electrical cables, hard drive disks, and many other electric parts are made of BPA. That's because it's easily recyclable. So when you want to upgrade your phone, it's no big deal. You can throw it out and get a new, or reuse the plastic in that phone. It's flame resistant, and it's a very good electrical insulator. Now, another application that's pretty prominent is in automotives. So if you think about a car, you want the car to be as light as possible to save on gas. That's where the high strength to weight ratio really dominates and makes BPA a very common material used in cars. And then also it's very cheap to produce unique shapes. So if you think about like a car's bumper, the hubcaps, most of the interior, it's all made of really odd shapes that come together, and out of almost any other material that would be pretty difficult to produce cheaply. And then for a unique application that you probably wouldn't even think of, BPA's or polycarbonate's actually used in glasses. So not only for the frames, but the lenses themselves. That's because polycarbonate is very shatter resistant, So you don't really have to worry about the lens breaking and throwing shards into your eye. And then it's also much clearer than glass, which means you can see just a little bit better in the dark. That concludes our presentation, and here are our references.